Hello. In this video, we're going to have a look at the roots of real polynomials. So a real polynomial is a polynomial with real coefficients. Now, in actuality, we're mostly going to concern ourselves with polynomials that have rational coefficients. But if we have a polynomial with real coefficients, the roots can be real or non-real. The fact is just that any non-real roots will have to come in conjugate pairs. This is comparable to the fact that if we have a polynomial with rational coefficients and then we end up with irrational roots, those irrational roots also have to come in conjugate pairs. The reason being when we're multiplying the factors together, all of the irrational or non-real parts have to disappear, cancel each other out essentially, and conjugate pairs do that. So if we start, for example, with a real polynomial, and again, I'm going to tell you it's a rational polynomial, it does have rational coefficients, and it has zeros of 3, 5i, and 2 minus 4i. As soon as I know that it has 5i as a root, I know it also has to have minus 5i as a root. This is like 0 plus 5i, 0 minus 5i. And as soon as I know that 2 minus 4i is a root, then I know that 2 plus 4i is also a root. The 3 doesn't need any kind of partner. 3 can be its own 0 because it is real, it is rational. There's nothing, I guess, ill-behaved about the 3. So the smallest possible degree of the polynomial, given that I know for sure it has 5 roots, 5 zeros, is 5. So if we find a polynomial with a minimal degree with these zeros, well, if I know those are the zeros, then I know the factors are x minus 3. I'm going to consider this to be a polynomial function, so f of x equals x minus 3 times x minus 5i times x plus 5i times, now x minus 2 minus 4i is going to be x minus 2 plus 4i when I distribute that subtraction, and x minus 2 plus 4i is going to be x minus 2 minus 4i. These two, the x minus 5i and the x plus 5i, are fairly easy to combine into the quadratic x squared plus 25. So if I have a pure imaginary root, it's coming from a sum of squares in the factors. The other two, well, those are, I can distribute these using classic multiplication, where I have a trinomial times a trinomial and then simplifying any I squareds that show up. I can also use the fact that I know in a quadratic the sum and product of the roots. So the sum of 2 minus 4i plus 2 plus 4i is going to have to be 4. And the product of 2 minus 4i plus, or sorry, not plus, I'm doing a product, so times 2 plus 4i. Well, that's conjugate pairs, so I end up with the difference of squares, which is 4 plus 16, so that is 20. Now, knowing that, and knowing that because in these factors that I've chosen, I have leading coefficients of 1, just x and x, I'm going to have x squared. So knowing that, I know that the product of the roots has to be the value of c in this quadratic, and the sum of the roots is the opposite of the value of b. So this is the quadratic. Technically speaking, once I had written that first line, I have the polynomial written in fully factored form. Classically, we're not going to want to leave it with imaginary numbers. We want to show that this is in fact a real polynomial, so we are going to have real coefficients. So I multiply together the conjugate pairs so that I get factors that have real coefficients. So I have the f of x equals x minus 3 times x squared plus 25 times x squared minus 4x plus 20. I really don't need to distribute any further than this. I don't need to get it into a fully distributed form because this form already shows that I have real coefficients.